All right, so welcome everybody. We're going to talk about Alan Wake's technology today, but before we start, can I remind you to sort of silence your phones and we can get started. So, my name is Markus Maki. I'm the CTO at Remedy, and I've been with the company for 16 years now, so since the founding. And I was managing the code team during the first 3 years of Alan Wake's research and production cycle. And my colleague here is Olli Tervo. He's our lead programmer, who has also been with Remedy since the very beginning. And he's one of the designers and visionaries on how the technology has been built and how we code things at Remedy. And Olli's going to be doing most of the talking during this next hour, but I'll just quickly cover some background first. So, we're going to be talking about how we build a big game and technology from the ground up with just 8 programmers. And what are the choices we made on the way to ensure that we could work efficiently. And we hope that this presentation can help you avoid some of the pitfalls we fell into, as well as get you thinking whether some of the ideas could work also for your team. And I'm not going to bore you with a long history lecture here, but to get the context for the talk, I think it's good to know a few things here. So, Remedy has always been a pretty skilled company when it came to tools and technology, and this was out of necessity because when we were established, the only licensable engine was the Doom 1 engine basically, and there was no middleware out there. And Max Payne was a long project for us with the evolving technology. We built the technology from the ground up for that, and then we followed up with Max Payne 2, a schedule-driven project with focus on execution and production values rather than big technological change. So while we worked on those 2 games, the gaming landscape changed quite a lot. And this pushed us to evaluate what to do with our next game, Alan Wake. It's also good to mention here that the Max Payne tech was very PC-centric. It was fully built at Remedy also, but it was very PC-centric. And it was pretty liberal for how acceptably it handled asset loading and memory allocation, and it really wasn't a first-class console citizen. But it was still ported to consoles by external teams. We had Rockstar Toronto work on the Max Payne 1 PS2 port, and we had Rockstar Vienna doing the Xbox port, and Rockstar Vienna doing both PS2 and Xbox ports for Max Payne 2. And for Max Payne 1, for example, our team of code ninjas flew to Toronto to help out with the port, and they had to resort to some bad Code Warrior magic and some really evil black books there to get it done. But while doing that, I think the teams, the Rockstar team and the Remedy team together did an incredible and impossible job to get the game running on PS2. The PS2 version used 200 megs less memory than what the game needed on PC. But still, the quality, the end result was way less than it could have been on the consoles if the technology would have been built from the ground up. So, the majority of the sales were on the consoles for Max Payne games, and we needed to build the tech first for the consoles. And in practice, even changing the lead platform or even requiring a multi-platform engine was it was too much for the old technology. But that's really not all. As we were sort of in pre-production for Alan Wake and as the goals for the game that sort of later evolved into Alan Wake, they were on high level. They were something that couldn't have been achieved with the previous technology. And it really sounded to us like it wouldn't make sense to retrofit everything to the old engine. And these goals, these requirements, first is going from level-based to open world. And we really wanted a smoother, more console-like experience for the gamers for Alan Wake. And well, maybe you could say, as after the fact that we perhaps went more with the trend rather than what were our team strengths, but anyhow, this was one big key for the new technology. We also looked at the sort of content production efficiency for level-based games, and mainly the art authoring time, so versus the time the player spent in the sort of areas. So we could have an artist detail one room for Max Payne for a week, and then the gamer should dodge past it in the blink of an eye. And that really wasn't efficient for a small team to work like that. And just one reason why we wanted to go towards open world. Well, we then came back to more towards a level-based game in the end, but done with an open world engine. But the open world engine then also meant outdoor emphasis. So Max Payne technology was an indoor tech, and for Alan Wake we sort of envisioned a new set of tools to build a large and detailed environment semi-procedurally with a small team of artists. Actually, our art director Saku Lehtinen gave a talk about the graphics part just before this lecture, so you can check that from the GDC vault when that becomes available. And then the new concept was going to be light-based game, and we had a pretty cool but totally static global illumination solution for the Max Payne games, and it really didn't fit the plans. So maybe a bit ambitious, especially looking at it from the hindsight. It's sort of, I think it's clear right now that we were a bit ambitious with the goals. So why didn't we buy tech from this guy? We looked at Unreal and other technologies out there, but this was actually before the targeted consoles, the 360 and the PS3 were even released. And we also had all of the three platforms planned in the beginning. We had PC, 360 and PS3. And I think it's sort of safe to say now that we had an overtly optimistic view of the schedule. And at that point, we didn't dare to commit to shipping a game on a third-party tech before the developers of that tech had shipped a game on each of those platforms. Well, 5 years later, on hindsight, I think that was the reasoning wasn't solid because these guys beat us to the punch easily. So what a third-party tech could have done for us is to reduce our moving bits and in the game production, and it could have been easier perhaps to get the project direction to be more focused and with that same time. I'm not going to turn this into Unreal 3 sales speak, so this is not to say we're unhappy with the end results going with our own tech. So we really could build the tools and the pipelines to match well with our team size and skills, and as well as match the sort of game concept, the light and darkness, with the technology, how it worked together. So our strategy was, we went with our own, and our strategy was one of focus. That's actually a really core Remedy element, well, if you forget the sort of the ambitious goals we had. So we needed to be top-notch in some areas, but we knew we couldn't do everything better than other developers out there. And for example, this meant that there's no multiplayer. We didn't build multiplayer into the engine. It wasn't in our core set of skills, and it would have been a huge effort. We also took the approach to license middleware wherever it made sense, even sometimes so that we didn't end up using all of the middleware we licensed for some reason or another. But that was a key part for developing the technology. And the big deal was the opportunity to go with Microsoft and drop one big technological effort, the PS3, out of the equation. And obviously that then changes technology risk to a business risk, but that would be a subject for a different talk altogether. To end my part here, I'm going to show this video. It's an internal tech demo from early 2004 that demonstrates the outdoor emphasis and the dynamic lighting we had going. And we were still exploring the game on another track, so this doesn't look at all like Alan Wake. So this is what the tech team came up with, and this sort of started to form the basis for the landscape editing and the landscape that you see in Alan Wake. But now it's time to pass the floor to Olli, who's going to tell you how we started to build the technology.
So, before just sitting down and starting to code furiously tech that would fulfill the requirements for the new game project, we decided to set ourselves some goals. While designing how to tackle any of the new challenges, we also decided to set ourselves some goals on what kind of code we'd want to write. One could say that in the brainstorming sessions we even created a shared philosophy about the coding style. And that philosophy lived in our heads, and now it's easy to say that we should have written it down. Later on, when we hired new programmers, we just ended up discussing the philosophy through with them, each one of them. And of course, we should have had a list of actual statements. This is stuff that every coder has opinions, and you have read about it like anywhere. And anyway, I wanted to give it a try and listed down some of the issues in our philosophy. We wanted self-explanatory code instead of commenting. We decided that class names and function names, they must be good, and it's perfectly okay to waste time in discussing the naming for important objects. Well, chosen names actually helped us a lot when working on new difficult concepts, or at least difficult for us. I think proper naming provides a lot more reliable information than commenting would. As an example, I'm a big fan of explaining local variables. And in many cases, those variable names, they can even have the most important words you'd have in the comments. So I think they're good. To avoid a mess of dependencies, we decided that every dependency must be justifiable. It's just so easy to add extra dependencies to code if you don't pay attention to this. Our rule of thumb was, if the include you're about to add would add an annoying array into your class diagram, then just avoid it in any way you can. And this was not only good for the compile times, but it was also good for the class design. Related to the previous goal, and actually this goes more to the syntax guideline side, but anyway, even if it's easier to use classes that in their .h file include everything you need for using them, it increases the compile time a lot if you do. So we did bite the bullet and we forward declared everything possible in the .h files. And wherever we use those classes, we had to have to add the few extra includes to the client code, but it totally paid off. Our compile times are really fast, or at least to my knowledge they are fast. That 1 minute, 2 seconds there, that's for the game application itself, and the libraries before that they took another minute, so it's 2 minutes altogether. We wanted to make everything easy to find. There will be no guessing where the implementation of a getter function is, if it's always in the .cpp file. One class per file, and so forth. We had rules for what should be found from where. It may feel a bit awkward at times, but on the longer run, it was really good. Another way of making the code easy to find was to split any classes that started growing. And I mean, we really did that, and not only spoke about it, as had happened with the previous projects. Also, we always kept the library structure in mind. So the content library just describes the data format, and any code that modifies the data will be somewhere else. With clearly defined purposes for different libraries, we were able to find the code quickly, and it made it easier to keep the source file small. For example, we had a class called vehicle defined in the content library, in the game project itself, and in the physics library. And they were all clearly part of the same concept. And the content library just described the data for the vehicle, and the game had all the visualization and logic code, and the physics had all the middleware-related code, but nothing else than middleware-related code. Also, we decided to follow our syntax guidelines strictly from the very beginning. It was updated to be perfect. And we knew that we'd all be so much happier if it would be easier to read the code and easier to refactor the code, and you wouldn't even need to think twice how to write something when you had a clear guideline for that. But anyway, that's about our philosophy, and that there is just a sample of our guideline, and I'm not trying to say anything like you should be doing any of that stuff, but it's a sample. The decision to write the new engine was based on a set of requirements for the new game project. So let's dig a bit deeper into those requirements. We wanted to provide as big world as we could without taking huge risks from the technology point of view. So we thought floating point accuracy, that would be enough for about anything within a 10 kilometers by 10 kilometers world. So that's roughly 6 miles per 6 miles. And we thought that if we split that to 512 meters by 512 meters, we'd have 20 blocks by 20 blocks in the world, and we shouldn't run into any weird housekeeping problems due to the amount of blocks. I mean, due to the amount of files or due to the amount of update calls or whatever issues you will have associated to each block. Of course, during the development, we ran into those exact problems. More specifically, we noticed that 512 meters, that's a huge chunk. Within a chunk of that size, you'll have only a few % of the data in the highest level of detail. In practice, you're wasting lots of resources. To give an example, the flashlight in the game that hurts the enemies only about 15 meters away. And a normal vehicle, that's not even drawn if it's more than 400 meters away. That's roughly a quarter of a mile. So to be able to have more detail where it matters, we had to adjust the granularity. So we ended up dividing the world into 128 by 128 meter blocks. And that meant 6,400 blocks altogether. So whatever you'll keep in memory or whatever you'll do with your CPU for each of these blocks makes a big difference. You have 16 times more of them than planned. Also, when you stream in new stuff in a lot smaller blocks, you'll have to seek a lot more files. Luckily, we had started optimizing our loading strategy just early enough, and we were able to cope with the increased amount of files. And also the higher granularity then ended up being a huge helper in the memory optimizations towards the end of the project. As we knew, we'd need dynamic lighting. We started evaluating what would be the best approach. And we were pretty satisfied with the static lighting quality we had earlier. But it would be pretty much impossible to mix and match that with the dynamic lighting. So we ended up deciding that we'll do 100% dynamic lighting. Even if that would mean a lot of rendering work to get everything to run fast enough and look good enough, we thought that it would be worth the invested effort. And it really was. It was a huge effort as expected. I mean, the render was restructured something like 4 times during the project. But we are quite pleased with the end result. Especially in the beginning, the lighting was pretty much driven towards the best possible visual appearance, making every single spotlight very, very heavy to render. At the same time, the light was supposed to be the most important gameplay element, making it quite obvious that the count of light sources that can become high. It took a good while to find the balance between the looks and the amount of light sources we could render quickly. So we found a solution from rendering all the point lights and spotlights as deferred lights. Well, this is not a lecture about lighting, but anyway, the idea is to buffer all the data needed to light the scene instead of doing all the lighting calculations against all the lights when you are rendering the objects. And later it will be then cheap to apply lots of lights to the scene. The directional lights of sun and moon remain forward rendered, which is the more traditional way. Reaching this solution wasn't easy because we had so much difficulties to get the deferred lights anti-aliased properly. Fortunately, with enough work on how to store the light buffers and how to reconstruct the lights, we were able to get them use deferred rendering. The directional lights, they remained forward rendered due to their omnipresence, which would prevent the really big performance gains. And also those bright, important lights, they deserve the better quality we were able to get through with the forward rendering. How about light-based gameplay? In the beginning, we had no clear spec for what the light-based gameplay would be, yet the engine should support that. So we just tried to write the engine so that we'd allow game logic to know about the lights. In practice, that meant knowledge about whether the objects are in light or not, and the AI pathfinding that was able to take the lighting conditions into account. That turned out actually to be enough to create good gameplay. So, those functional goals, they were a big part in the decision to write the engine from scratch. And in addition to those, another important aspect was to get the technology more console-friendly. The related goals they were pretty simple, but not at all easy to reach. So let's check out a few of those. There must be no dynamic allocations. That sounds strict, doesn't it? We were quite afraid of the memory problems after seeing the console ports of the previous game, and we wanted to avoid fragmentation and especially any surprise memory allocations that would cause the game to run out of memory. Well, anyway, initially this was really our goal, and of course we knew that we'd have to be flexible with it at some point. But anyway, with that as a goal, we knew that we'd be able to build a memory management that would be good enough for shipping the game. So soon after starting, we realized that obviously, yes, we need to be flexible with that. And we modified the rules so that not just everything is pre-allocated into pools, but everything that makes sense is. And in addition, we do want to make the allocations in the streamer thread while loading in new objects and not liberally in the game thread wherever you like. The biggest exception was going to be the renderer. The most important reason for the whole streaming technology was to be able to allow to stream the big memory hogs like textures. And some flexibility was needed for allocating them. So renderer had its memory allocated in one big chunk, and it was to be used for the textures and for the index and for the vertex buffers. And renderer had its internal memory manager, which defragmented the memory on fly with GPU. That worked out really nicely, and there you can see the video memory being debug visualized. Green is textures and yellow is geometry, and those little black spots there are unallocated, and if this was live, you'd see them disappear soon due to the defragmentation. As the consoles were going to be our main platform, and they had multiple threads available, we knew that it would be a good idea to take that into account. So we used one thread for the streaming and another for the game logic and rendering and one for the physics and few others for smaller purposes. It was relatively simple. I mean, there wasn't much of decomposing work into tasks or something like that. And it was causing actually quite manageable amount of difficult bugs, or at least a lot less than I was expecting. The bugs were difficult, but the count wasn't really that high. So actually, I don't have that many interesting findings here to talk about, so let's skip forward. Must avoid seeking. Previously, on PC, we were simply random accessing files on disk. But it was obvious that we'd have to rethink our I/O handling totally to be able to run from the DVD. As explained earlier, the world was split into chunks, and some of the data was split with tasks, which needed different assets in the same area but on different times. The idea was to load everything you need for one chunk in one go. Later on, we started realizing that we'd have immense amount of duplicates in memory if all the textures, if they were packed into each and every chunk that uses them. And especially when we added the granularity of the spatial splits, the problem went worse. The first version of the streamer actually just loaded the assets straight from the disk with random access. And even though we always had this I/O goal in mind, we actually never wrote the real packaging of the assets. That was scary. We knew that we'd not be hitting this goal nicely. And as I guess almost anyone else making console engines, we ended up optimizing the I/O a lot towards the end of the project. We did it mostly by sorting the file access so that when you had multiple files to load, we just loaded them in the order that would cause the least amount of seeking. And of course, we optimized the DVD layout according to the access patterns, etc. Also, by having strict control over the I/O, we were able to play back video cinematics while we were loading new locations on the background. So even though cutting into a new location needs the biggest amount of assets, it was simply hidden behind the cinematics. No parsing while initializing. On the previous engine on PC, it wasn't really that bad to load a script file and parse it on fly. It actually allowed a decent iteration time for certain types of content. Then again, if you parse a lot of files on fly, you may end up with a lot of temporary memory allocations and at least a bit longer loading times. So compared to preparing the data offline as much as possible. So to avoid that, we simply parsed all the scripts and all the data definitions. We parsed them in the exporting, and we aimed at exporting them in a format that would be as close to a memory image as possible. So loading any basic data on the game side would go through the same pipe. That is, loading the data from disk into a content class, and when the data is in place in memory, we'd just fix all the pointers, and it should be good to go. No conversions, no validity checks, nothing like that parsing kind of work was needed in the game side. From pure programming perspective, that worked out fine. Loading was fast and robust, and the data was good. The offline processing allowed validity checks to be done there without worrying about the execution time or memory allocations. So we had lots of good tests there in the offline process. On the other hand, one could say that we created a rather rigid system, which didn't allow rapid iteration. Any value you'd have to change permanently, you'd have to change that in the source data and export it to the game. That sounds horrible, but in practice it wasn't really that bad, since we added a nice way of quickly searching for good values for those definitions in the game. Basically tweaking almost any of the values you'd have in the data definitions was possible. And tweaking with the sliders, that was fast, and the actual trouble was getting the data back to the source data in our tools side. And as changing the values permanently, that remained a bit awkward. That's one of the things we aim at improving a lot in the future. Well, this isn't exactly console-centric anymore, but anyway, this was one of the big requirements. Must be able to get the game world in pieces. Watching how the console ports of the previous game, the data was cooked for something like 20 hours, and in a code-heavy project, I think that's a bit more okay. But for us, in a data-heavy project, we couldn't even think about similar downtime between being able to properly test the data and iterate it further. So for those reasons, we wanted to keep the world exporting in a condition where it's always possible to just export the piece you are working on. And it should become a part of the full world data without going through a global cooking process. Well, that sounds pretty much like an obvious choice. Of course, no one wants a long iteration loop. But then again, we didn't really realize the amount of code work that decision caused. Rather than having a few big problems, we had a huge list of small problems, and well, of course we had to deal with them. Let's say if you wanted to have a global list of certain types of objects in the world, that wasn't simple at all compared to a global cooking process where you just go through all the data and collect whatever you needed. We just have to think about the place where to store the data and how to make sure it's not off sync and so forth. Basically, almost everything could go pretty easily off sync when you're working with pieces that are exported on different times. So some potential optimizations became harder or were missed altogether. So finally, after years of working and fulfilling these requirements and meeting those goals, and of course working on a few other issues, it finally we got it all together. So that build 757 right there, that was an excellent build. Now Markus will talk a bit about the development cycle.
All right. So I'm going to start by saying nobody really plans to do a 5-year game and project, and we didn't either. So I'll summarize some of the observations from the development cycle. I think the issue number one here is really clear. We had too many sort of variables to consider at once. And we had a new IP, we had new technology, and we had a new ambitious game design. And this does just tackling one of these at a time would have been easy. Tackling all of them together when each of them affect each other was really, really hard. And that definitely slowed us down. Open world wasn't in our team's comfort zone, and we had clashes with the dramatic storytelling. And only when we went to the details of the problems, we started to see all of the issues we had. And I think you could also say that the line between pre-production and production was a bit too vague with us. And some of the design decisions were also flip-flopping as the sort of IP and game design matured. And this caused, for example, us to build 3 separate player melee prototypes, and then player melee didn't end up to the game at all. So some time wasted there. Another issue for us was the sort of iterative nature of the development process. And it was really fast for us to get the first iteration into the game. And I'd say after the first year of development, we pretty much had every component in the technology and in the game. But it was always the very first iteration, and nothing was really finalized. And this was also because the game design wasn't really firm enough to call anything final. And only later we started to learn the distance between almost there to complete. And we were always after a really polished end result, and it was easy to underestimate the time it took to polish things. And the iteration speed also slowed when we got closer to the desired end result because there were more dependencies. Let's take vehicles as an example. The first version we built didn't have enter and exit animations for the player. The player didn't sit in the vehicle. The engine's sounds were sort of placeholder, nowhere near final quality. The controls didn't feel exactly right, and it was easy to, for example, roll the car over with no gameplay handling for situations like that. But still, we felt that, hey, we have vehicles in the game, we have vehicles in the technology. That was BS. Basically, compared to the final version, the initial version took maybe 10% of the total development time. So it was sort of harder for us to see the big picture at times. But I think in the end we were able to adapt and meet goals very well, and we had a small but very efficient team. And one of the reasons there is that we kept the code work quality driven constantly instead of hacks on top of hacks, and this helped us a lot. We fixed bugs constantly. We didn't let them pile up to be, I think the most open bugs we had during the project, if you don't count the sort of final QA period, was 30 code bugs. So we always fixed bugs when they appeared, when they were reported by the team. And we also kept breaks from adding new features to the game and improved the technology structure instead. And this helped us keep the sort of basis stable and enabled us to continue adding feature. And the end result is something that Microsoft test team said that Alan Wake was the stablest game they've ever seen during a QA phase. And I personally think it's pretty incredible that we shipped our first 360 game and 2 big DLC packs without a title update. So usually nowadays when you put the DVD in to whatever game, you get the title update even before sort of you boot it up the first time. One claim I could also make that we probably could have released the game earlier from the tech side if the gameplay feature set had been locked earlier. So the tech side was on a very, very solid basis. And we're happy about a few things in the tech. I think the tech is really nice to work with, and it's like the compile times are fast, it's very readable, it's very well structured and divided to libraries, and it's easy to go in and fix things, refactor things if you want to. And that's because of the discipline we had during the development. The streaming obviously is very flexible and advanced. You can stream any type of game object, not just textures and meshes. And the streaming could still handle open world requirements easy. And as Olli said, the memory management and deferred rendering with AA, I think they were really, really cool things. But there were a few things, of course, that we could have done better and differently, and I'll let Olli go through a few of the biggest issues.
So here comes a short list of few issues we'll be giving some focus in the near future. Or actually, we've started already on a few of these. So the technology is already there, and of course it can be extended, etc. But the biggest need for the next project is good content. And I mean, the content has to be created from scratch compared to the technology which can be reused a lot. So making the content creation easier is a big focus for us. Another thing already mentioned earlier is the iteration time. Obviously, if we would have built if we know the amount of iteration or tweaking all the values all around the game, we would have built some mechanism to talk back to the tools from the game. And well, now we have the system like that. The communication pipe is open and we're improving that a lot. Also, make the optimization phase a little less painful, we try to improve the content budgeting. It's not as easy as it may sound. I mean, at least we haven't been able to combine the knowledge about how the game can optimize certain situations with the tools so that we'd be able to actually enforce the content budget on the tools side. I think that would be the key to really create optimal content. Also, there are a few open world concepts left in the engine that could be simplified a bit. For example, we had multiple code paths for handling mesh objects, depending whether they are gameplay relevant or just decorative. And I think that was just extra complexity. In a linear game, we ended up treating all the objects equally. So it was a good source for bugs and miscommunication. We'll be improving that. Also, obviously, we aim at keeping the technology clean. So even though it was in a good shape when the game shipped, we have dedicated some time to clean it up further after the project. And we are trying to avoid degeneration by keeping and improving the coding style philosophy. That's still done by discussing about it. And maybe someday we'll figure out a better way of storing that knowledge, and maybe you'll have some good ideas you'll tell us. Yeah, I've heard lots of good things about unit testing. So many of you probably have your opinion on it after trying it out, but for us, it's still ahead of us. So we'll at least give it a try on some large piece of code, and let's see how it works for us. So, even though I think this rewrite was a success, no, we are not rewriting the engine again. Currently, I'm thinking we can overcome all the problems in the engine by just refactoring those components that need it the most. Then again, in the beginning of Alan Wake project, we faced reasons that were big enough for the decision. So who knows, maybe someday big enough reasons are in front of us again. But until then, we are not rewriting the engine. Thank you.
So, thank you. We will have time for questions and we'll gladly answer anything. But before that, I'd like to remind you that can you please fill the evaluation forms and hand them on your way out. And if you have questions, you can come to the microphones or I can try to hear it from here. Okay? Thank you.
I'd like to hear about the breakdown of your team. You said you only had 8 programmers. Is that correct?
8 programmers, yes.
And were they most generalists? Or, were they able to roam around whatever area of the game required work? Because that's really not a lot. That's a small team.
Okay, so the question was, we had 8 programmers. Were they generalists or were they sharing work? I think most of them were specialists in a sense that we had a fairly dedicated rendering programmer, fairly dedicated animation programmer, a couple of the base tech guys, tools guys, and so on. But I think all of the guys had been at Remedy for, I think, average 9 years. So they knew the technology inside out pretty well. So it was easy for us to sort of flex a bit if somebody was ill or something like that. Any other questions? So the question is, would the technology, how easy would it be to get it running on PS3? Well, maybe $1 million. It wouldn't be easy, but we think it would be doable with a reasonable sized team, and if they had enough time.
I wouldn't be rewriting the engine for PS3, but just trying to use the same engine.
Yeah, but the problem would be, I think, then sort of how to coordinate the development of the engine while porting it as well. So obviously it wouldn't be easy at all.
Hey, just a quick announcement. If you guys have questions, please use the microphones.
Yeah.
I have one. Did you stream code logic as well? And if so, how did you handle the side effects of that?
Sorry,
Like
did we stream?
code logic, like script code, that belonged in another chunk?
Yes, we did stream scripts.
Okay.
Yes.
So how did you handle the side effects of, say, you had a currently running script that affected something else in the world?
So how did we handle the streaming? Olli?
So the script was basically when you have one episode of the game running at the same time, all the script for that is loaded at the same time. And that was the granularity. So basically when you saw one episode ending and the next one starting, then you'd get in new script. And there was no referencing between the old episode and the new episode.
Okay, thanks.
All right. Any other questions? Come on. Well, okay.
Hi. You mentioned that there were 8 programmers. How many people on the content side?
On the content, so how many people did we have on the content side? Well, I think our animation team was maybe 1/10 of Assassin's Creed. We built the whole sort of 10 by 10 kilometers or 100 square kilometers of landscape with, help me. Okay, Saku, our art director there.
One half, you have to repeat it for the recording, but about 1.5 times per minute for the content update. So investing on tools.
Yeah. I'll repeat it for the recording. So, yeah, we had really streamlined tools to build the environment, basically semi-procedurally. And as I mentioned, Saku's talk was about that. I think the whole sort of environment art team was just only a couple of guys, basically. And, well, obviously we did outsource characters and vehicles and assets as well, but, yeah, it was really tight team.
That was for landscape and the rest of the environment.
Yeah.
4 or 5 guys.
Yeah, 2 guys for landscape, 4 or 5 guys for the sort of placement of objects and house buildings and so on. Any other questions?
Yeah, I had a quick question. It seems like it took 6 years to make this title. Would you say that's an average amount of time? And for future titles, do you expect to spend that much, or is it going to be like less? Would you say?
So would I feel the development time was average, or should we do it quicker?
Well, 6 years seems like a long time to me.
Yeah, it was a long time.
No.
It was a long time, and we are trying hard not to do that again.
We will be quicker in the future.
Yeah. But yeah, it's sort of creative work and sort of concepting new IP that it just takes its time to mature. Any other questions?
If I may add to that, art director, I just answered a similar question, so I have it freshly in mind. Like what was special about the development cycle of Alan Wake, I believe, is that we had our pre-production much more visible than most game productions usually have. And we had a small team, so what would be a disaster in a team of 200 people, we had, when we started, maybe 25 people doing the pre-production. And we published the product really early. Of course, there were missteps, but still that was visible to people, whereas in a big company where you have multiple projects, there's typically projects in pre-production, and then only the last 2 years are visible for the general public. So it is longer in time than average, but it also may seem much longer than it really was.
Okay. Thanks, Saku. Anything else further? You can come and talk to me. I'll be here for like 15 minutes after the session. So if you don't want to ask in front of audience, you can talk to me later. All right. Thanks, guys.
Thanks.